Hi and welcome to this next video from the integration section of the Year 2 A-Level Maths course, and we are working through some integration techniques. Particularly in this one it's integration by parts, and you'll have seen in the previous video the basic idea behind that technique. What we're going to do now is have a look at a couple of extra bits. There's one bit that's a sneaky little trick that you need to be aware of, and the other one is a really useful result that we haven't come across yet, and there they are. First bit is this one here. Integrating expressions where the original integral is part of the integrated expression, which again probably won't make a lot of sense till we look at it. And then the second one is we're going to have a look at what happens when we integrate ln x, and we're going to achieve that result, which is a result we haven't seen yet, but we're going to achieve that by integration by parts. So on we go. So generally the integration by parts, it says there, will only work when you've got one term that's a polynomial, so it will break down via differentiation. So for example, an x squared becomes 2x, which eventually then breaks down to become 2. And the reason for that is because within our formula we've still got a product here. So you need this product here. Essentially you need v to become a constant, so we've only got one thing to integrate and we haven't got that product. But there are exceptions to that. So here we go. Let's have a look at the first sneaky little trick. So we're going to go e to the power x cos x. Now if we have a look at those two things, that certainly isn't in the form we're talking about up here, because differentiating e to the x will give you e to the x, differentiating cos x will give you minus sin x, then that differentiates becomes minus cos x, and you just go round in circles with sin cos, sin cos, sin cos, and it will never break down. So this bit over here is always going to have a product in it, and so it seems like that's just not going to work. But bear with me, let's see what happens. So let's choose u to be e to the power x and go through the process. There you go, du dx is the same thing. dv dx is cos x, we need to integrate that. We end up with v being sin x. Put it all together, so there's my uv minus the integral of v du dx. And there we go, we now need to find e to the x sin x. Okay, and so you're thinking, well, you know, we've still got this product here, so we're still going to have to do this entire thing, but just with this bit here. So let's proceed onwards for now. So now what I'm doing is just looking at the second integral here. So I'm just going to just put this to one side for a second. Let's just do this bit. So let's go again. U is e to the x, du dx, there we go again. dv dx this time is sin x, integrate that, we're going to get minus cos x. And so the integral of e to the x sin x becomes minus e to the x cos x, my uv, minus the integral of v du dx. There we go. Notice we've got a minus going on in there. So there we go, there's that bit tidied up. Now, again, we've still got this product going on, so you're thinking to yourself, well, for goodness sake, we're just going to keep going round and round in circles, but here is where the sneaky trick comes in. What I'm going to do is, we know that e to the x sin x integrated becomes this expression here. So what I'm going to do is put this expression back into here. So let's do that. That bit there is going back in. So we've got that. Notice we've got a minus and a minus going on there, so let's just tidy that up. And that's what my integral now looks like. Okay, so we're looking at this thing thinking, well, you know, I've still got, okay, that bit's okay, this bit's okay, they're integrated, but I've still got this term over here, which is a product, so I've still got the same issue, and I've already been through 2 rounds of integration. What the heck is going on? Well, here we go. Now, if you'll notice, the product that we're trying to integrate now, this bit here, is the same as this bit over here. So this was where we started originally, and this is now contained with it. So what we can do is just do a bit of rearranging. What I'm going to do is take this thing here, shift it over to the other side, put it with this one. So now on the left hand side of my equal sign, I've now got 2 lots of the integral of e to the x cos x. So now the last thing I've got to do is say, well, if I've got 2 lots of the integral of e to the cos x dx is this thing here, if I just want 1 lot of it, which is what my original problem was, all I've got left to do now is simply just to divide by 2. And there we go, and you can see just in here I've just done a little bit of factorising as well. I've taken the ETX out. Again, that's just my OCD nature in mathematics. But that's a kind of fairly groovy trick, because that's basically got around the fact that this thing here is never going to break down, and it allows us to do the integrating, and there we go, we've got it sorted. So that was one trick. I have seen that appear on a couple of exam papers, so it is one to watch out for. It doesn't appear very often, but it is just one to be aware of. Right, moving on. The second thing that I'm going to do with my integration by parts is come up with a result for integrating ln x. Now, ln is a real groovy one. We saw that differentiating ln, we know we end up with 1 over x, but up to now we haven't got a way to be able to integrate it. So that's the thing, that kind of the missing piece in the puzzle as we are at the moment. So let's have a look at what's going to happen. You might be looking at it thinking, well, this thing here, integration by parts, is for use with products. Clearly ln x is not a product, it's just a function in its own right. Well, here we go, let's have a look at what we're going to do. So there's my integral of ln x, that's the result I'm going for. What I'm first of all going to do is write it as a product, and the way I'm going to do that is by writing it as 1 times ln x. Now, normally when you do an integration by parts, you want the function that's going to break down, i.e. the polynomial, to be what you're going to use for u, which would normally be this one here, but this time I'm going to use ln x as my substitution for u. So if u equals ln x, differentiate it, and the reason it's going to work is because when we differentiate ln, we get 1 over x, so it's become a polynomial. Let's just work it through now and see what happens. So we've got, that means dv dx is going to be 1. Integrate that, that means v is x. So put it all together now. So my integral becomes, there's my uv, minus the integral of v du dx, v, which is that, du dx, which is that. Hopefully you can see what's going to happen. We're going to get some cancelling going on. So there we go. The x's cancel, there and there. We're left with just this thing here, just becomes 1. So now the final step is just to integrate 1. So we've got x ln x minus the integral of 1, which is just x. And there you go. There's your result. So when you integrate ln x, the result you get is x ln x minus x. And there you go. Now, again, so any time that you see in the exam an integral that requires integrating ln somewhere along the lines, then the way to go about it is to set it up as a product and do your integration by parts in the way we've just demonstrated there. Cool beans.